Welcome, everybody. Wow. Glad you can all hear me. Thank you all for coming. It's a very impressive crowd here. Some very well-known scientists. It's nice. I see some visitors from like as far away as the state of Washington, Greece, other places. It's great. All right, so we're here to celebrate Bill's retirement. God bless you. You made it. You made it. Bill arrived here, what, over 40 years ago? A little over 40 years ago as a postdoc, and then became an assistant professor, tenured professor, full professor. He even served as chair of our department for a while. He's had a very long, illustrious career. And the best news is we're going to have a reception after this. So after, hearing Bill talk, we're going to go to the Salt Auditorium, which is to the right, about 100-something feet, and we're going to have a reception. We're going to hear a couple small speeches. And I'm going to do a little slide presentation later, so I'm going to keep this short. And the slide presentation should be a little fun, and we could all make comments later on. So without, I know you didn't come here to hear me, so Bill, come on up and tell us about Overturning, late small, 40 years as a Seagoing Oceanographer.
It's great to see everybody. Thanks for coming. Yeah, I'm retiring. I'm actually retired already. So, actually, when the idea for this talk first came up, I think it was Arthur said, "Yeah, Bill, you should definitely give a career-ending seminar." And I'm like, I better wait till after I retire to do that. So I retired at the end of last year. It's safe now. I can do that. I've seen a couple of these retirement seminars now by some of my esteemed colleagues, and so I was going to try and kind of follow the format for those, which I think the school also kind of wants for legacy purposes. They video these now. Which puts more pressure on me. So that, I'm going to talk a little bit about, what got me interested in oceanography in the first place, and some of the early experiences I had that kind of set my path, my research career, and then some science snippets on the way. We have a bunch of scientists here, so I have to talk about a little bit of science.
Can you speak into the microphone?
Turn on the mic. I do it, but I don't want to do this.
Yeah, there you go.
A longer mic.
Can we put it up there?
Maybe they have a portable mic so that you can be heard.
All right.
Okay, well, I'll bend down a little bit for you, John. Right, so how did I get interested in oceanography? I've always interested in people's stories about this because they're all different. Mine was actually a remarkably straight path. I grew up doing a lot of sailing when I was young. My dad was an avid sailor and sailboat racer, and it's a passion of his, and it became a passion of mine too. And so, when you're sailing, one of the big things in your sailing strategy is currents, like tidal currents. So you got to learn that stuff. And I was always kind of fascinated with the complexity of tidal currents and things like that. Well, there's that, and then I knew I wanted to be on the water because of sailing, live on the water because of sailing. And then, I don't know how many of you remember this, but when I was a teenager, the Jacques Cousteau TV series came on, which made the ocean seem really mysterious and cool. And, I don't know, I think it had a lot of influence on me. It made me think about, what the word oceanography, learn the word oceanography. And I think it had a lot of influence on other people in my generation too, who lived in marine science. So that's kind of like how I started thinking about it. And when time came around to get serious about college, my dad took me down to see the dean of the marine school at the University of Delaware. We lived in southeastern Pennsylvania at the time. And we talked for a while, and the dean said, "I think you should consider being a physical oceanographer," which I had no idea what it meant. And then he told me that, you can't get a 4 degree in any school, which is true back then. You could not. There was no place to get a degree in marine science that was 4 years. He said, you got to go get like a physics or math degree, and I'm starting to sink in my chair, and then you got to go to graduate school. And it all seemed like a bit scary, but I figured, what the heck, I'm going to go for it. So I went to Florida State. I got a physics degree. They had a good physics program. They had a good sailing team. Didn't really want to do in college. And then after that, I applied around to graduate schools, and I got accepted at URI, great school. And yeah, people here from URI, TSO. And of course, right across the harbor is Newport, Rhode Island, one of the great sailing meccas of the world. So this is an easy decision, you know. So here I am in physical oceanography. That's how I got into it. So. Let's see. Yeah, so graduate years at URI, I worked with Randy Watts and some with Tom Rossby as well. Randy was my major advisor. There's a beautiful Bay campus with their research ship, the Endeavor there. Bottom used to be white, but more recently it's been blue. And yeah, I really had a great time there. It was a wonderful place to go to school. Great group of professors. Learned a lot from all of them. Melvin Stern was one who I learned my geophysical fluid dynamics from, very well-known theoretician at the time. So it was a great experience. For my thesis, back then we were still in the Cold War with the Soviet Union, and there was a lot of money available for Gulf Stream research. There's concerns about submarines being able to hide in the thermal fronts of the Gulf Stream, so there was a lot of interest, particularly from the Office of Naval Research. And so I studied Gulf Stream meanders of the current system, and just, Randy had deployed this small array of inverted echo sounders, and I'm not going to go into how those work, but basically I can tell you where the location of the Gulf Stream front is, kind of along these lines, and as you could watch the meanders propagate through and see how fast they were propagating and what their growth rates were. And so we got new data on that, and then try and figure it out. I ran this instability, I developed this instability model. This kind of shows results from that, where we predicted the growth rates and phase speeds of these meanders, and it worked out, agreed pretty well with observations. So it's like, this was like, for me, a really valuable early lesson in using observations and models together to try and attack problems, that can really advance your understanding that way. And also, we looked at deep currents too, some rudimentary, small deep current meter moorings we had out. And I was trying to look at the vertical coherence of meanders, and it turned out there wasn't much. There was this whole other variability in the deep ocean dominated by what's called topographic Rossby waves, bottom track topographic Rossby waves. It kind of blew me away, and it made me really curious about what's going on in the deep ocean. Kind of carried forward from that. So here's some pictures from the graduate school days. That's me, believe it or not. It's a lesson to all you, even old people were young ones. And there's my lovely wife, Libby, sitting right here, who is also a physical oceanographer. We're out on the
Looks like the endless summer.
out on the RV Endeavor there, and we met the graduate school and got married. Went to see a few times together there, and a couple other pictures. That's me sitting up on top of the A-frame. I can't believe they let us do that. We never be able to do that nowadays. And then one of our favorite pastimes, once the deck was clear and mooring stuff, was playing broom hockey, deck hockey with brooms and XPT caps, and be in the middle there, trying to guard the zone. Anyway, it was a great time. I think we went to see I went to see 8 or 9 times while I was there working with Randy and Tom Rossby, and so really cemented my love for seagoing oceanography by the time I left there. So then, we came down to Miami. Libby got a postdoc at CMAS. I got a postdoc in the MPO department, working mainly with Fritz Schopp here. So these are some of the key kind of people who influenced me and worked with. They had just finished the STACS program in the Straits of Florida at that time. I believe a long time ago. STACS stands for Subtropical Atlantic Climate Studies. It was a NOAA program run by Bob Molinari here. Wonderful colleague and friend. And one of the main goals of that program was to calibrate this submarine cable underneath the Straits of Florida with, so they could use using the electromagnetic induction theory to continuously monitor the Straits of Florida transport. And so that was a big experiment with current meters and everything. That's what I worked on with my postdoc. Tom Lee was here at the time. Worked a lot with Tom, Kevin Lehman. As I said, Bob Reyna was part of the STACS program as time went on. We used to have great meetings. Rain, I remember those meetings. We'd all argue with each other. Don was a big influence on me. Otis Brown was heading the remote sensing facility at the time. And Klaus Ruth, dear Klaus Ruth, one of my dear friends, great theoretician, always loved talking to him. So it was a great introduction to a new group of people. So a little science here. So because as I was going back and thinking about what I've done and what I've been involved in, it kind of really came to me that how stuff that we take for granted now, we just did not know that. And it doesn't seem that long ago, but it's amazing what we didn't know. I'll give you a couple examples. So this is a time series, this blue line, of the cable-derived transport of the Gulf Stream right off the Key Biscayne. Well, it's further north, but the Gulf Stream runs through Key Biscayne, and all these black dots are the calibration cruises that NOAA did to keep that cable in calibration. And this time series runs till today, so it's 40-some years long. And you can see all the variability that's on all kinds of time scales in that transport. And this, I kind of worked on the first 2 years of this data, the SACs, to look at the kind of the high frequency days to weeks time scales. But in addition to the, and just to give you an idea for people who don't know, we have this unit for transport called SPIRS, which is a megaton of water per second. And it's unfathomable amounts of water. So just to put it in perspective, this 30-some SPIRS that flows through the Straits of Florida is the same as 10,000 Niagara Falls. So it's massive amounts of water. And so besides the variability, there was interest, even some, we didn't really know what to make of this mean number back then, 31-something SPIRS. There was well-established, theory of wind-driven circulation then that said we had showed ocean gyres, kind of showing schematics here, that formed strong western boundary currents like the Gulf Stream. And you could predict the strength of those western boundary currents, like the Straits of Florida, by knowing the wind stress, strength of the wind stress in the interior of the ocean. And believe it or not, we didn't really know the wind stress that well. I mean, we had decent winds, but we didn't really know perfectly how to convert them into wind stresses because of drag coefficient parameterizations and stuff. And so it wasn't clear whether this, 30 SPIRS was made sense with these kind of wind-driven circulation. And actually, kind of look at some of the wind fields that came along that were better, just about that time, it really suggested that the Florida Straits should be carrying a lot less flow than that, more like 20 SPIRS and not 30. So that was one basic question. We know the answer to that now, we didn't know it then. And then this picture came out, the famous picture, the Great Ocean Conveyor Belt by Wally Broker in 1987, which kind of focused our attention again on the thermohaline circulation in the world oceans. And in the Atlantic over here, that we call that cell the Atlantic Meridional Overturning circulation, AMOC now. And it's basically got a warm upper layer that collects waters from the surface layers of the Indian and Pacific Ocean. It goes all the way northward through the basin, gets cooled, sinks up here in the Gulf to a deep current, and then comes back to the south, deep in the ocean. And it was not a brand new idea, but Wally coming out with a kind of refocused attention on it made it, we all kind of didn't realize we didn't know that much about this. We know the strength of the cell. The estimates for this Atlantic branch of it range from 10 to 25 SPIRS. Nobody had really measured it. And furthermore, results were showing that this upper branch didn't really go as it's drawn here, but it actually was coming over and probably coming into the Gulf Stream system, which is probably the main reason for the discrepancy between what we were seeing in the wind flow. So these flows were somehow, interacting with each other, and it raised a bunch of interesting questions, like how does this thermohaline flow, this upper branch, make it through all these gyres? They're not independent circulations; they have to coexist. What about the deep limb? Nobody had by that point actually measured the deep western boundary current anywhere in the ocean. So all these questions, kind of came up, and it sent us in the stats program initially in a bunch of different directions at once. We went to the tropical Atlantic here, did a couple of programs there, SACs, and then later an North Brazil current experiment that I'll talk about later. That was followed by an extended program in the Caribbean passages that Doug Wilson and I did together. Kind of looking, these are focused more on the upper branch of this overturning circulation. And then we also went out and set really the first mooring array in the deep ocean boundary current here east of the Bahamas. All about, kind of, these at least at almost at the same time to try and, answer some of these questions. So, I'm still a young scientist here. Only, I think I just started as assistant professor, and we put this mooring array, this first mooring array we put out in the tropical Atlantic, right here, 3 mooring array across this feature called RSMAES. And here's a cross section of it. And this offshore mooring is at the base of the continental slope. This produced this record. Some of you may not be used to looking at what we call stick plots, but on this plot, the length of those sticks is proportional to the strength of the current, and the direction is north to straight up. And, so it's got an angle to the right, it's east. This is still my favorite single current mooring record ever. It's a mind blower. Look at this. At the surface of the ocean, it's incredibly periodic signal. Almost looks like a tidal record, except that the periodicity is like 50 days. And then, down deep in the water column, all of a sudden you have this steady southeastward flow. It turned out this mooring was right in the core of the western boundary current. So I wrote a paper about this upper ocean flow. And then I wrote another paper about this deep ocean boundary current flow. And I remember when reviews came back from that paper, one of the reviewers said, are we to expect 2 papers from Johns for every mooring you deploy? And I thought to myself, man, I wish I kept up that ratio. That's not good. I did not. Anyway, so the upper ocean part of that signal turned out to be North Brazil current rings. This is when North Brazil current rings were discovered, some of the biggest eddies in the world's ocean. We had to kind of piece together from our current meter data and some patchy earlier images from the coastal zone color scanner satellite that had beautiful signals from Amazon river water that's kind of wrapping around here and defining this. But this is a sequence of a ring shedding. And the North Brazil current that comes up here is part of that equatorial gyre I showed before, wind gyre, retroflex, and it's popping off these rings. Boom, 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 boom. That's what that signal was. So that was really interesting. It's one of these things that it's amazing we take for granted today. Look at, we had altimetry now, gridded altimetry. You would know this in a second by making a movie of altimetry, or even any of our decent, eddy resolving numerical models that show this. But we didn't know that then. We had to, we didn't have those tools yet. So it's popping off these eddies, and then we went back and did a whole program focused on them later because we found out that this cross-equatorial flow in this upper branch of the AMOC was coming in the North Brazil current here. It was almost later work we did show that it was the entirety of it was in this North Brazil current, and some of it was going out in the interior and then finding a different pathway. But almost half of that upper ocean thermohaline circulation was carried by these rings. So it's like the rings become a transport mechanism rather than a steady current. It's a pretty cool finding, and then these rings go on to kind of crash into the southern Caribbean, and the water gets dispersed, and ultimately gets into the Gulf Stream system. So that was followed by a bunch of work, observations and modeling work too. A student at the time, David Fratantoni, went to Woods Hole later, that used models and observations to kind of describe these 3 different kind of pathways, coastal currents, rings, and kind of an interior pathway, all of which converge in the southern Caribbean during this thermohaline flow. And then this program that I did with Doug over many years, and Doug was really the one who led it, kind of confirmed that all of this South Atlantic upper ocean water was pouring in the southern passage of the Caribbean into the Gulf Stream system. And these wonderful, average pictures from more than 20 cruises that we did in these passages, showing this red stuff is inflow of that South Atlantic water into surface. So that was tropics, what we found out there about the kind of the interaction of the overturning circulation with the gyre there, and how this all worked. And then up off of the Bahamas, we set this array of current meters starting, in 86 really, or 87 was really the first main array, and I was just a fresh assistant professor. Did this work with Tom Lee mainly, and NOAA was involved. They were doing hydrographic work off the island, off the Bahamas too. That we maintained for about 10 years with funding from, there was the World Ocean Circulation Program came along at that time, providing part of the funding. NOAA climate change programs provided. At that time, when the World Ocean Circulation Experiment started, there were certain key locations that were designated to be measured, and this was one of them. This array was called ACM1 in Atlantic. So we measured that for a while there. And yeah, we found the deep ocean boundary current, beautiful current here. Also found a near surface Antilles current as part of the wind-driven circulation. But there's a problem. If you start accumulating this transport and this deep flow here in the boundary, that deep ocean boundary is carrying something like 35 surface flow. It's like at least kind of twice what we thought the strength of the overturning circulation is. So the idea was that when we went out there was, hey, let's measure the deep ocean boundary current. We can get a direct index of the overturning circulation. It's not complicated by all this upper ocean gyre stuff. But that didn't work either. There's offshore recirculation or something going on here. We know a lot more about it now. One of my more recent graduate students, Tiago Vila, did a really nice job looking at what's going on with this. There's a deep recirculation gyre here. And you can kind of see that the transport climbs back towards a smaller number as you integrate across it. But so I guess the lesson that we learned at this time was that this plus the fact that the Gulf Stream, for a while, we thought we measured the Gulf Stream as an index of the gyre circulation. No, the thermohaline circulation is passing through it too. And then the deep ocean boundary current now is there's something else going on. This is not a direct index. So this kind of all began to lead to the idea that it's not going to be that simple, the ocean. It's not going to make it that easy. We're going to have to figure out a way to measure all the way across the width of the whole basin to really get the strength of the overturning circulation. Which ultimately led to the RAPID program, which happened years later that we were involved with here. So it's just interesting to review how we came to the realizations that we kind of know very well now. All right, I want to take a moment to talk about our ocean technology group. This is our mooring team here. It was here when I arrived. It's still going. It's an incredibly talented group of technicians that really does all the work for these deep ocean moorings, and there's only a handful of groups in the country that have the capability of doing this, and we're one of them. So just to give you perspective too, this is like a typical mooring off of Abaco, Bahamas, in the deep ocean boundary current. It's not quite 5,000 meters deep, but that mooring is like a little more than 3 miles tall. These are really, tall moorings. By comparison, here's the Burj Khalifa, the world's tallest building in Dubai, 2,700 feet. So the moorings working that in terms of, and that's how deep the ocean is there. And it's quite a process to deploy these moorings. I have a little, when we do it, we like to work fast. So just a little time lapse of the mooring deployment. You kind of start, some distance away from where you want the mooring to be, and start paying out the surface for, and then you attach your instruments and float clusters like they're doing here, put them in the water, and then you're slowly steaming toward your target drop site where you want to put the anchor. When you're there, then you put these big, you make them out of railroad with anchors, and boom, there it goes. Down the mooring goes and plants itself for a year or more at a time. So it requires a lot of skill to do this and do it safely. I just have to say that group has been such a resource for me over these years, and to other investigators here at the school. I wouldn't have been able to do half of the things I did without that group. All right, a couple other things that we were involved in, kind of high-profile things with the mooring team. Around that same time, there was this big SYNOP experiment. Arthur, you'll remember this well. In the Gulf Stream, again, really trying to look at Gulf Stream predictability. And one of the new developments, the cool things that happened in that was this was right about the time that acoustic Doppler current profilers first came out, which are routinely used for measuring currents in the ocean now. And we here at Rosenstiel actually bought the first two, we call them ADCPs for short, acoustic Doppler current probes that were built by RD Instruments. We built, Fritz Schock bought the first two. And the first deployment of them was in the Indian Ocean, Somali Current. Fritz and I wrote a paper about that. And then for this experiment, which was together with Rhode Island, Woods Hole, and other, I think mainly those were the teams involved, I bought several more of these ACPs, and we put them in these large syntactic spheres of the cavity so they could profile remotely the upper ocean current. Measuring like the ocean current near the surface in a really strong deep current like the Gulf Stream was basically impossible until this time, because you could build a mooring with current meters off the surface, but it would get blown over by the current. You didn't have the measurements. So the idea was that you stop the mooring at several hundred meters below the surface, you put one of these ACPs in it, remotely profile this. This is the first time that it's done. It's routine, it's routinely done all over the world in oceanography now. But that system with the float and the cavity of the ACP was actually designed by Mark Grant. One here. I don't know if Mark, you here? He's going to come. Anyway, one of the lead engineers at the time. So and then it allows you to make pictures like this of the structure of the Gulf Stream, including the surface layers. So yeah, I'm kind of proud of the fact that we here at Rosenstiel were the first ones to do that. That technique was really developed here. Other people have done it. So that was and then we went over to the Kuroshio. This was also during the World Ocean Circulation Experiment. There was another key array labeled PCM1 in the Western Pacific. Very similar setting to the Straits of Florida, and Tom Lee and I teamed up with Taiwanese investigators to do that. Did all the work on Taiwanese ships. It was really interesting seeing how they do things differently. I have stories I could tell about that. But it was kind of benchmark measurement of the Kuroshio system that was really was a valuable experience for us too. And the student who was working on that project, Dong Zhang, is here from PNEL in Washington. He wrote some really great papers on the variability of that current system and its role in the heat transport and ocean heat transport in the North Pacific. In fact, I think there's seven or more of my former graduate students that are here that came for this. And thank you so much for coming. We've been sitting in my office, job owning all morning today, having a lot of fun, remembering old times. Okay, then a little bit of a change of pace, which I really, part of my research career, I really enjoyed. A good friend of mine, Steve Murray from Louisiana State University, had been trying to measure the flow through the Bab el-Mandeb Strait, which is the entrance to the Red Sea from the Indian Ocean, for years, and there was too much. Yemen was always having a civil war. Yeah, big news, right? It was difficult to do. It was one of the key world, straits in the world ocean that really needed to be measured, never been measured. And so there was a kind of a break in the action, and it was the time to do it. He invited me to participate, to do the program with him. And so we did, and we did a couple of cruises there, set this really large current meter array in the Strait of Bab el-Mandeb, and made the first current meter measurements of that strait. And then right after that was over, our group by themselves went up and we did a similar program in the Straits of Hormuz, which would be pretty hard to do today. It was a smaller experiment, but luckily we knew we couldn't do any measurements on the Iranian side of the strait, but we were only on the Omani side. Fortunately, that's where the deep outflow channel was, so we could see what was going on. But so both of these seas are kind of like little microcosms of the overturning circulation in the Atlantic. They're dense water is formed in them. What happens is relatively fresh surface water is coming from the Indian Ocean. There's huge evaporation in those basins because near deserts. Water becomes really salty, sinks, and then it flows back out as a dense gravity current into the Indian Ocean. And it tags the whole Indian Ocean with this high salinity signal at depth. And that the circulation, the strength of the circulation was unknown, and so it was wonderful to be able to get there and make those measurements. And then, so we basically provided the first direct measurements of the exchange rates and the deep outflow and season and cycle. And that was followed by some really, really, nice modeling work by a couple of the students I had on the project. Searantis Sofianos did some great modeling of the Red Sea using the Micon model. It was also, importantly, was developed here by Reiner Bleck and Eric Chassanet. Big contribution to the world of modeling. And so Searantis made a model for the Red Sea, and this picture shows the surface inflow, complicated gyres and boundary currents, all leading the colors of the salinity leading, as it goes to the map to the northern end of the Red Sea, and it just sinks and comes back out as a salty outflow. And Searantis already came all the way from Greece, believe it or not. He heads the physical oceanography division at the University of Athens over there right now, so he's done well for himself. And another student, Feng Chia, did a really nice set of modeling and studies for the Persian Gulf as well. And this top slide shows the surface inflow of the fresher waters coming to saltwater in the northern Gulf. Bottom one, identified these outflow pathways from the dense water formation region. So these were both really pioneering modeling studies of these basins. So the observations, again, together, like you make a kind of a really constraining measurement, like this, gives you the power to go look at models and trust it. They match that, trust the output, and use them. So that, they did a wonderful job with that. So we enjoyed that, and then we followed that doing an experiment together with Amy Bauer and some other people from Woods Hole to go look at more detail of that Red Sea outflow. And what happens is that as that high salinity water comes out of these basins, it starts accelerating down the slope as a gravity current, basically a river underwater. And once it gets going fast enough, it becomes unstable and it mixes turbulently with water above it. And what happens is its transport grows as it gets diluted. So this is a picture here along this section near the bottom. This particular outflow is channelized into these two kind of channels, and near the bottom of that you can see these high salinity waters coming down these two channels and the mixed water above them. Yeah, and so this is a key process in overturning circulations. This entraining Molly Behringer, with Jim Price did the initial work on this problem. These gravity currents, typically double their transport, and that determines how much deep water is produced. So in the North Atlantic, very similar process happens in the deep limit of the ocean circulation. You get these dense overflows from the Nordic seas. They turbulently entrain, and that's what determines what the strength of the lower limit. So it's a really important process. And in a situation like this, this allows you to study it on a scale a little bit more accessible than the North Atlantic. But one of the really important outcomes, apart from the observations here, was the follow-on work that was done by Tamai Asgafman and students and Eric Chassanet, where they used this data set as well as some others to try and develop better parameterization for these large ocean circulation models, so they could do this better. And it was a really important improvement. That was great collaborating. Again, data leading to models that improve everything. I just loved it when that worked out. It was really important development. Of course, there was some drama on this particular project. There were 2 cruises on this project, and I unfortunately, or in retrospect, maybe fortunately, couldn't make the second cruise. I had something else going on. Amy Bauer, who came down from Woods Hole here, was the chief scientist in that cruise, and they were attacked by pirates off in northern Somalia in that cruise. Actually, a rocket propelled grenade was fired at the ship. It was the Maureen Seagoing, and luckily it went in the water and didn't come anywhere near the ship. But very scary moment for everybody aboard. As far as I know, it's the only time a U.S. research ship has been attacked by pirates. But Amy, you have that. And actually, it was all her fault. she was trying to trace this outflow as it went down along the southern coast of the Gulf of Aden. And it was kind of really important to do a station really close to northern Somalia, like a little too close. And so out comes this boat, a guy holding an RPG, and I'm not sure if they were pirates or just some militia trying to chase away the big U.S. ship or something. Anyway, they ran away, they got away, everybody was safe, but it was a bit of a scary moment. Okay, well that was an interesting chapter. I really enjoyed that work. But back in the Atlantic, things were kind of heating up, so to speak. Right about that time, the National Research Council came out with this report called Abrupt Climate Change, Inevitable Surprises, which kind of raised the specter of a collapse or a major slowdown of the AMOC and to a level higher level than people had been thinking about before. Followed shortly thereafter by this movie, which dramatized that situation, which a lot more people saw and probably paid attention to than the NRC report. But this idea is this is still a thing. This figure right here shows a bunch of most recent models from the IPCC coupled model intercomparison project, where these are climate projection models, and this is their AMOC. There's a lot of variation in initial strength of it, but you can see this decline that happens a lot. In fact, all of the models that were run with high emission scenarios and would run beyond 2100 collapsed. So there's a lot more concern that this, may not be a super low probability event. And even if you don't believe in models, right about the same time too, Harry Bryden wrote a paper based on trying to estimate the strength of the AMOC here at high latitude around 24 north in the Atlantic based on single hydrographic sections. And his estimates shown here showed what looked like a pretty precipitous decline in the overturning circulation. So all these things kind of led everybody to say, wow, we need to get on top of this. We need to start measuring this. And that's really what led to the RAPID program that we've been involved in since 2004. Our group, Chanel Poe was with me, Molly Berenger, and other people were involved in it. Basically, a partnership between NOAA, us, and UK scientists at the lab in Southampton, where the Gulf Stream was measured by the cable and calibrated, as they've been doing. We set our deep ocean boundary current array out here again, and the UK team put a bunch of other moorings across the basin. And I won't go into details, but this allowed us to measure across the whole basin and really capture the strength of this overturning circulation. Okay, so big surprises here too. This is the first year of data from that array. It shows in red strength of the AMOC over here on this scale. And the other components of it were the Straits of Florida transport, a little break in the cable at that time, the interior gyre flow, and the southward flow and the recirculation, and then the cement transport and the surface layer. But what was shocking was the amount of variability in that, how time variable that circulation is, that overturning circulation is. And here's a little box showing all the spread of the values that Brighton had made over the year, and they easily encapsulated by the variability that we saw in the first year. So it was clear that you can't monitor the circulation by doing occasional hydrographic sections. You need to measure it continuously. And most of my energy in the last 10, 15, since this time and other programs has been focused on this overturning circulation in the Atlantic and measuring it, documenting how it might be changing. Okay, fast forward. Here's the full record, 20 years, with monthly time scale, monthly data, and annual filtered data. And there's a lot of variability, but there is now a trend that is actually a statistically significant trend. Barely, but it tells us that if you believe the statistics, that the AMOC is declining. It's about one spurt per decade, so 2 spurt drop over that time period. Doesn't seem like a lot, but if you put that on this little blue line right here on the figure I showed earlier is our trend. 26 north. And you can see it kind of follows the general trend of these models. Now, myself, I feel like I would need to see at least another decade or maybe even 2 of this before I really believe that we're on that trend, because there's internal variability. But it's interesting that it does show that. And it's really important to know what trajectory the AMOC is on, because depending on how much it slowed down or collapses, it's going to have huge disruptions to our climate system. Global temperatures, particularly around the North Atlantic, monsoon, global precipitation patterns, drought, regions of drought that'll get worse. Just huge impacts if that collapses, maybe even something we haven't anticipated. So it's really kind of important to know if this is happening or not, or if it's on that trajectory. I think it's important for this work to continue. Since after the RAPID program got started around 2008, the U.S. Interagency Program, Climate Variability Program, called CLIVAR, pulled together an AMOC science team. There was everybody that was working on this problem to really kind of accelerate the knowledge of the system. And one of the early recommendations from that team was that this should be done at more than 1 latitude. We need to know, we need to be able to confirm, what's happening at 1 latitude that's consistent with other latitudes, and see how coherent the variability is between latitudes and on what time scales. And so since then, there have been several arrays installed, and people at NOAA are very heavily involved in the South Atlantic Array. We've also, besides RAPID, been heavily involved in this subpolar gyre array called OSNAP, Overturning the Subpolar North Atlantic program. It's a big program involving USPI's Woods Hole and other institutes in the U.S., European Institute, Canadians, all working together. The Dutch are involved in it too. And the region right here in the Iceland basins, where we kind of are part of that program, again, looking at these entraining gravity currents that produce the deep water. In this case, these are dense outflows from the Nordic seas that then form what we call Iceland Scotland overflow water. So we've been really focused on that part of it. So here's a plot at the bottom of the 10-year time series available so far from that in terms of the overturning strengths. It's looking at the black line. You can break it up into the overturning circulation across the Labrador Sea between Canada and Greenland, and then the eastern part of the basin between Greenland and Scotland. But it's not really showing any trend yet. But very consistent magnitude with what we see at RAPID, about 17 or so. That's consistent. The question right now is these arrays are really, really expensive to maintain. And people are working really hard to try and find out or figure out how to make them less expensive using autonomous tools like gliders and other things. But I think we need to keep measuring it. There's also a possibility. One would hope that we have a lot of new models that assimilate data too. We have reanalysis models or really great computer models that assimilate all of our satellite data, all of our Argo data. One would hope that those models assimilating all the available data would be able to keep track of the system for us and wouldn't have to put out these expensive arrays. But at this time, there's still a lot of differences in those models run by different groups across the world in terms of the strength of the overturning circulation, its variability. Variability doesn't necessarily match up with the observations that we've had. So I guess my parting thought on it is that until those models all converge and give us a result that we can trust, we should keep measuring because it's really important to know where it's going. So I think I'll end there. I want to thank a couple people besides all the students that I've had the pleasure of working with over the years and postdocs. There's a core group of technicians and research associates that really are the ones that make this work possible. And the Ocean Technology Group and people I've had as my research associates in my lab, and the ones that really do the work, and really, in a sense, are kind of the glue that holds everything together. Mark Graham here, led the mooring team for many years. Rob Jones was with us for many years. Eduardo Jardines here now. Cedric helps us out a lot. OMC. Reiner Zantop for many years. Sorry, I couldn't find a slide without your chin cut off. John Molina, Adam Howe, Joe Brettel. Now, these are the people that are really, for me, that they're my heroes. The ones that have really made it possible for me to do what I've done. And to everybody else sailed with and had the pleasure to work with, thank you for the memories. I'm retired now, you have to take it easy on me.
Oh, yeah, I can hear you. Yay!
Anyway, I hope that wasn't too science heavy. My original idea was okay, I will tell one story first. No, go ahead, Joe, that's your question.
Okay. Several slides back where you showed the long-term trend, and what you said was a statistically valid trend. I noticed that the amplitudes are much larger.
Yeah, it's fun to zoom in.
The amplitudes are much larger earlier in the record than they are later in the record. Any explanation for that?
Well, there's a seasonal cycle, and it was really, really strong in the first 5 years of the program. And then we had, you can see that there's this huge interannual anomaly right there in 2009, 10. That was a lot was written about that. That was the first, kind of big wake-up call that it's more than just seasonal variability. And after that, things kind of were a little different. There is a paper I know that's coming out soon talking about the change kind of in the seasonal signal, but maybe it's more than a seasonal signal in the monthly average data that's higher amplitude. It's a good observation. Part of that is a larger seasonal cycle in those early years.
Talk a little bit about the changes in the funding environment. As I've legendarily, there was massive support for ONR in the 80s and 90s. It kind of disappeared after 9/11. And how has this whole program managed to keep going with that?
Yeah, that's a good question. It's always hard when you're trying to do these kind of programs that cost a lot to keep them going. It's just been. This particular program has been funded almost exclusively by National Science Foundation. It's been a strain for them at times, but I can say that every proposal that we've written from the U.S. side is, it's really well reviewed. People think this is important, and so we've been lucky to get really good feedback from reviewers that it's also. It's been pretty readily funded as we've gone along. But I don't know if there's been ups and downs in each of our. I would say one of the things that I have noticed the most, and a lot of us are ONR investigators, or have been, and that's a little more volatile. It has been for me in terms of the research that they fund. It kind of oscillates between certain different emphasis, so that I don't know about overall funding levels, but it's been a challenge sometimes for me to fit in with the large scale kind of stuff that I do. It's kind of become less important. It's like the opposite of research lately. I don't know. Maybe I've been lucky. We've been okay with the funding, so I haven't really had to fret it too much.
Bill, what advice would you give to the young scientists here in the room?
For me, it's always been just what's the next logical question. I mean, that's you know, and then go for it, you know, figure out how to attack it. I don't know how to say it any differently than that. I believe there's a trend, you know, in all of our science as we get better models and satellite observations, and we're getting a more complete picture of the large scale circulation phenomena. I think, you know, a lot of the research is moving down to smaller scales, to sub-mesoscale, even, you know, beyond mesoscale to fine scale frontal mixing processes that pushing the, you know, areas where the numerical models are challenged to do it right. So I think, you know, there may be a trend in the, you know, funding towards supporting that. As I don't want to say that the exploration phase of large-scale ocean circulation is over. It never will be, I don't think. But and even in these AMOC programs, what amazes me is even though the goal is to measure the AMOC, we are learning so much about the whole circulation system and the deep ocean boundary currents, and you know, there's a ton of other things that are learned as you go. So, new discoveries even in the Oceanographer program about the strength of the deep limit of the circulation, you know, that we didn't know before. So there's still plenty of exploring to do, but I think there's going to be more of a focus on maybe smaller scale processes. Must be time for party.